Now we will see a method, namely coordinate method for finding discharge rate. See here, there is a pipe and in which a jet falls down. Let the throw distance is x and the height of the pipe is y. And you can very easily understand that the velocity of throw and the distance of throw and the height of pipe are interrelated. If the velocity of throw is more, then the jet will be thrown to a larger distance. So we can establish a relationship between Vx and x and y. And if you are able to establish a relationship between Vx and x and y, we will be able to easily find out what will be the discharge rate that is coming out of this pipe, because x and y are measurable in the field. So from x and y, if you are able to find out estimate Vx, then obviously the discharge rate is equal to velocity of flow into cross sectional area of flow. That you know that Q is equal to velocity into area of cross section of flow. So the area of cross section of flow can be also measured in the field, and we will be able to find out what is the discharge that would happen in this process. So before we derive a relationship, we will do a very small hypothetical experiment. We will take a vacuum room. We will take a vacuum room. It is vacuum. It is a vacuum room, and a person is holding an object, and he allows the object to fall down. Let us assume that the time taken for the object to fall down from here to here is, let us assume that t1. Let us also assume that he throws the object for a little larger distance, and let us denote the time taken for the object when it is following a projectile path. For that also we will assume that we will represent that time to be t2. So what will be the relationship between time t1 and time t2? Why did we take vacuum? Is because only then we can neglect the air resistance. When we do this experiment outside the room, which is not vacuumized, then air resistance will come in and the discussion becomes a little complicated, and we will not be able to derive a simpler form of equation. So why we have assumed a vacuum room is to eliminate the air resistance. Okay, so when we do not have air resistance, when the object falls down from here to here, and also when the object when the object is thrown with a force, when it follows a projectile path and it takes a different path, and during that time also, during that process also, how much time that object will take to reach the bottom. What is the relationship between T1 and T2? I say T1 and T2 will be equal, but most of us will not accept that T1 and T2 will be same, because when an object is falling down from here to here, the distance it is passing through is a smaller distance. When it is passing through this path, the distance it is moving is a larger distance, and people will think that T2 will be larger. But if this hypothetical experiment is done in a vacuum room, T1 and T2 will be definitely equal. Now I will explain why. We will take the first case. When the object falls down from here to here, straight down. Why does that object falls down? It is because of the gravitational force it is falling down. So how the velocity will get increased, the velocity increase will depend on the gravitational acceleration. So the gravitational acceleration is the only cause that is causing the body to fall down. So g is constant in this case. Let us assume that it takes time t1 for this case. Now you take this case. As soon as the body is given a force, it is given a velocity. When it is given a velocity in horizontal direction, while it is in flight, while it is moving along the projectile path, there is no other force acting on there is no other horizontal force acting on the body. There is only one vertical force on this also, only one vertical force that is acting on this body. That force is again gravitational force. So again the fall is because of gravitational acceleration only. So in this case also gravitational acceleration only causes the fall to happen. So in this case also this body will reach the bottom at the same time because no other force is causing motion here, motion in the vertical direction. So if we assume that, or we will assume here also this process also occurs in vacuum. So in order to, why do we make that assumption is to get a simple form of equation. So if we do not make that assumption, air resistance will come in. If air resistance comes in, then the derivation becomes complicated, and our intention is to derive a very, very simple form of equation. So the time taken to fall from here to here and time taken from here to here, both are assumed to be same. Okay. So now we will derive a relationship between this t and y and the velocity of fall. So what is t? This t is distance divided by velocity. You know that time is equal to distance divided by velocity. In this case, distance is y. Velocity at the start of the fall it is only 0. Vy is 0 and Vy keeps on increasing because it gets accelerated. So when it reaches down, what will be its velocity? Its velocity will be equal to g into t. T is the time taken for the object to fall through this distance. So what after all g is? G is change in velocity per unit time. So change in velocity per unit time into time will give you the change in velocity from here to here. So initial velocity is 0. So 0 plus gt is your Vy. So this velocity becomes average velocity because the velocity of fall is not constant. The velocity at start is 0 and velocity at the end is gt. So y is equal to 0 plus Vy by 2 Vy, so that is gt divided by 2. So now we get t is equal to y divided by 0 plus gt divided by 2. So what after all it is equal to t is equal to 2y by gt. So this t, if it goes here, then t squared 2y by g. So this is a one equation we have derived. So for this same time t, we will also express another relationship in terms of horizontal distance. horizontal distance of throw. So in the same time t, horizontal distance of throw, distance is x and velocity is vx. In this case, velocity remains constant. In the vertical fall, velocity, it was not constant. It started with 0 velocity and it ended with the gt velocity. In horizontal case, what happens is the horizontal velocity keeps remaining same, and of course there will be horizontal velocity decrease because of the air resistance. And since we assume that air resistance to be 0, we can take that Vx to be constant here. So we get T to be distance divided by velocity. If you look at this is also in T, this is also T. So now we can equate that to be x divided by Vx to be equal to root 2y by g. T is equal to root 2y by g. So this is a very useful relationship. You can see from this equation that x, y are measurable in the field. G is the acceleration due to gravity, that is constant, and Vx alone is unknown. So once you find out velocity Vx from this equation, you can measure the cross-sectional area of flow and you can find out the discharge rate. Keep in your mind that when we derived this equation, we assumed that air resistance is neglected. So since we neglect the air resistance, what will happen is the discharge rate, what you get out of this formula, will be little less than the actual discharge rate. So if the air resistance is when air resistance is existing really in the field, what happens is it reduces the x distance. Because of the air resistance, it will fall at a smaller distance. So that only you will measure. If the air resistance does not exist, then your x will be little larger, then the discharge calculated will be more. So because of that, when you really measure discharge rate using measurement of x and y, the discharge rate what you will get will be little smaller, and that discharge rate can be taken as a conservative estimate of the discharge. Thank you.